Good day and welcome back for the third part of our discussion on Green's theorem. And let me begin with a reminder of the statement of Green's theorem. If we have a simple closed curve C with a positive orientation, the line integral of the form p dx plus q dy, which recall is a line integral over a two-dimensional vector field with component functions p and q, can be expressed in an equivalent form as a double integral over the region enclosed by that curve, call it d, of dq dx minus dp dy. In our previous examples, we've started off with a difficult to evaluate line integral, applied Green's theorem to express it in terms of a simpler double integral, and then evaluate it. In this example, we're going to go in the opposite direction. We're going to start with a double integral and turn it into a line integral. So let's go ahead and apply Green's theorem to find the area enclosed by the given ellipse. So note, just in terms of the ellipse itself, x squared over 4 plus y squared over 9 equals 1. That is an ellipse that has x-intercepts plus or minus 2, y-intercepts plus or minus 3. So it is just a smidge taller than it is wide. And we would like to find the area enclosed by this ellipse. And before going through the work, let's think about the answer we expect to find. We've been asked to find the area enclosed by an ellipse. And in my experience, when I ask a classroom full of students, what is the standard area formula for an ellipse? Just like that, I met with a lot of silence. But note, this really is familiar if we just think of modifying the area formula for a circle. So let me just kind of note to the side what we'll hopefully find out. If we have an ellipse, x squared over a squared plus y squared over b squared equals 1. So we're thinking that we have an ellipse that has x-intercepts plus or minus a, y-intercepts plus or minus b. So I'm going to draw it similar to what we see to the left, a bit taller than it is wide. The area enclosed by this ellipse is going to be of the form pi times something. But let's think back to a circle. A circle is really just a special instance of an ellipse when a and b are equal to each other, and the area would be pi times radius squared, so pi times a squared, say. But if a and b are different, we need to multiply pi by both a and b. So it's really just kind of the generalized version of the area of a circle we've used many times. Furthermore, let me remind you that we can come up with a parametric description of this ellipse, and we will even make sure to give it that counterclockwise or positive orientation. And that parameterization is x is equal to a cosine t and y is equal to b sine t. And if we allow t to vary between 0 and 2 pi, that would be a parametric description that goes one time around the curve in that counterclockwise direction. So let's see if we can combine these ideas together. What we would like to do is apply Green's theorem, as the problem has instructed us to do so. But in order to apply Green's theorem, we somehow need a line integral over a vector field. So let's just think about what our starting point is. We want to know the enclosed area. Let's call this region D. It would be the double integral over D of the function 1. And if we are going to be applying Green's theorem, this quantity 1 is representing what we see inside our double integral on the right side of the Green's theorem formula. It would be dq dx minus dp dy. And that dq dx minus dp dy must be equal to 1. So in order to apply Green's theorem, we have a question to answer. Can we find a vector field F of the form p comma q with qx minus py equals 1? And the answer is yes, we can in fact find infinitely many such vector fields. So it really turns out to just be a matter of picking one conveniently. For example, I could make qx1 and py equal to 0. So if we allow q to be x, that would make qx equal to 1. And if we set p equal to 0, just to make it as simple as possible, then of course qx minus py is equal to 1. And this is a choice that works. Similarly, we could choose q so that qx is 0, and choose p so that py is minus 1. Then qx minus py is 0 minus a minus, or a positive 1. So you can see rather quickly that there are going to be many vector fields that work. One where I think the computations work out quite nicely is if q is 1/2 x and p is minus 1/2 y. So this is another scenario where qx minus py is equal to a positive 1. And we will use this third possibility simply because the computations work out nicely. So in this case, our vector field f would be given as p comma q. So minus 1/2 y comma 1/2 x. And what we would like to do is apply Green's theorem, but now kind of going in that reverse direction. So Green's theorem implies that the double integral is equal to the line integral over the curve C, where note C is the curve above bounding the ellipse, but with a counterclockwise orientation. And our integrand for the line integral will be p dx plus q dy. So that is p dx plus q dy. And in order for us to evaluate this line integral, we need to go back to our methods we've previously discussed. That is, what is a parametric description of the curve? But using our observation from earlier, we can use a parametric description of the curve given by x is equal to 2 cosine, y is equal to 3 sine. And the parameter value will vary from 0 to 2 pi, so that we go around exactly 1 time in the counterclockwise direction. And in order to evaluate this, we turn it into a line integral over that parameter t, and then we just substitute in for each quantity that we see in the integrand. For example, each x becomes a 2 cosine t, each y becomes a 3 sine t, the dx will be replaced by x prime, the dy will be replaced by y prime. So note, x prime is minus 2 sine, and y prime is 3 cosine. Substituting in, we have minus 1/2 times y dx. And note the dx is going to become the x prime, so minus 2 sine t. Plus 1/2 x, so 2 cosine, dy. And the dy becomes the y prime, so 3 cosine t. And if we go ahead and do a couple quick simplifications, note the minus 1/2 and the minus 2 cancel each other. The 1/2 and the 2 also cancel each other. So we have the integral from 0 to 2 pi of 3 sine squared plus 3 cosine squared. If we factor out the 3, And note sine squared plus cosine squared is 1. We have the integral from 0 to 2 pi of 3, which is equal to 3 times 2 pi, which is the desired value, 6 pi, which is the area enclosed by this ellipse. And to summarize, it's important to note that Green's theorem is most typically applied to evaluating a line integral by expressing it in terms of a simpler, easier to evaluate double integral. But that is not always the case. Here's an example where we started off with a double integral, and we used Green's theorem to express it as a simpler, easier to evaluate line integral. In order to do so, we had to come up with a vector field f so that our integrand was the dq dx minus dp dy required by the statement of Green's theorem. In our next video, we will continue exploring this topic of Green's theorem. So stay tuned and take care.